Hello everybody out there, and thanks for joining us. This is Marcus Levy reporting to you live as the moderator for today's webinar. I'm president of the Multicore Association and chairman of the Multicore Developers Conference, which by the way will take place on May 21st and 22nd, 2013 in Santa Clara, California. I'm also founder and president of Embassy, the industry standard benchmark organization. Chances are good that if you're attending this webinar, you have an interest in making your multi-core DSP go faster and be more easily portable and scalable to future generations of processors. In short, this webinar will examine the challenge you'll probably encounter in this endeavor and will offer a way to deal with these challenges utilizing a graphical user interface to simplify and visualize the topology and inter-process communication strategy. So why is the Multicore Association hosting this event? As you'll see over the next 40 minutes or so, the presenters will demonstrate how to instantly apply our MCAPI specification to support a flexible system design. Before I introduce our speakers, let me take 23 seconds for a few housekeeping items. First, on your screen you should see a little box that you can use to enter questions. If you're having logistics issues, you can also use that box to communicate directly with our staff. For questions related to the webinar, we've saved time at the end for a Q&A session. We'll also post a recorded version to our website and send out a notification shortly after the conclusion of this webinar. Our presenters today are Sven Bremer and Debbie Greenstreet. If you've been in this industry for a long time, actually dating back to 1983, you might know Sven from his days as CEO of Diab Data. Today, Sven is recognized as a multi-core pioneer, being directly involved in this industry for a better part of the past decade. He's the CEO and founder of Polycore Software, a board member of the Multicore Association, chairman of the MCAPI Working Group, and a significant contributor on the MRAPI specification. Similarly, Debbie has been involved in the telecommunications market for more than 20 years, previously working at companies such as Raytheon and Telergy Networks. She's been at Texas Instruments for almost 12 years now, where she's the strategic marketing director of TI's multi-core processor business. Now, I'm certain that you're going to enjoy this webinar and you won't need any enticements to stick around, but we're going to sweeten the deal. At the end of this webinar, we're going to have a drawing, and a lucky winner is going to receive a Barnes & Noble Nook Simple Touch with glow light, and you'll delight in knowing that it contains an 800 MHz TI OMAP 3 processor. So without further ado, I'm turning it over to you, Debbie. Are you ready?
Thank you, Marcus. First, I'll give a brief overview of our agenda for the presentation portion of our webinar today. We'll touch base on a few applications just to put things in context and talk about first the market requirements for optimizing programming for multi-core SoC solutions. We see several aspects to this solution here, and one, of course, is starting with the silicon. We'll talk a little bit about the state-of-the-art of multi-core SoCs. And then Sven will move into some of the software aspects of programming for multi-core and get into some of the challenges first. Take a look at the perspective from the applications and what the requirements are there and ideal situations in applying these applications to multiple platforms. Then taking a look at a programming model, what's the appropriate model here to be able to program for these multi-core solutions. Next, of course, including standards. We want to make sure we have a standard method of doing all of this. We'll get into looking at a use case and how this can actually be applied, both the standard, the programming model, to the SoC. And of course, none of this would be complete without looking at tools, ways of being able to implement this very easily and efficiently for the engineers. And then finish up with an example of being able to port from one platform to another using this method that we will just described. And then, of course, we'll follow up with some conclusions before we get into the Q&A portion of the webinar. Just to set the stage a bit, we'll take a quick look at here some applications that will be truly benefited by having a paradigm of programming efficiently and optimizing for multi-core SoCs. These are just a few of many that I'm sure you're experiencing as users and that we see in the market, but some that do require multi-core SoCs, high-performance type applications. solutions like mission-critical functions, radar applications, for example, use a lot of very large FFTs, and of course the more that can be done in a given amount of time in a given amount of space optimizes the radar solution both for commercial and military applications. Test and automation solutions are looking for compact, low power type functionality yet high performance to be able to move around and take out in the field and get high performance testing on a variety of telecommunications equipments. We're seeing a lot of activity in high performance computing. This is some of a shift from the traditional RISC-based processing into leveraging DSPs for optimizing math-intensive compute challenges, signal processing requirements, and things like that typically supercomputers have been relegated to in the past. Imaging applications as well, both embedded machine functions as medical imaging areas where, again, signal processing and math-intensive type operations are required, especially to get lower power and more compact solutions. In the video and audio space, especially in the existing infrastructures, telecommunications, lots of needs for transrating and conversion of various different standards for the audio and the video applications. There's also a need for these to be able to upgrade it in the future as the standards evolve, as the need for higher definition solutions are applied to this space, and so definitely portability to higher performance platforms is a requirement in this space. Seeing a lot of activity in video surveillance, leveraging analytics functions to do video surveillance solutions, and if they're efficient enough and low power enough, they can be placed in the endpoints as opposed to having the video streams pumped back to a central server. Of course, in the wireless base stations, very compute-intensive solutions. The 4G type 3GPP standards require lots of performance, lots of computing, as well as digital signal processing programmability capabilities for multiple antenna algorithm functionality. So what are some of the requirements then that are being dictated by these applications as they relate to multi-core solutions, software, and silicon? Certainly performance in computing is one of the key factors, whether it's FFTs, other types of signal processing. The desire for increased computation capability, along with being done in the most efficient way, perhaps even faster than today, is highly desirable for a high-performance application. We're also looking for green solutions, obviously not for the benefit of simply just the environment, but also for lower power solutions requiring lower overall power costs, and in many cases being able to have a much more portable system with a much lower power footprint. We're looking for consolidation, reducing the size in many cases and almost always reducing the cost of the solution. Obviously this is beneficial for the end users, but certainly for the manufacturers of the equipment as well, being able to offer cost-effective products into the marketplace. All these functions are very desirable to have scalability in their solution offerings. In other words, being able to have perhaps a low, mid, and high-end solution to offer to the customers and users versus one single type of platform, and to be able to bring those at different price points and performance points. All these features are obviously desirable only if they're able to be brought to market relatively quickly and in an optimized way. Given the economy today, it's certainly businesses must operate very efficiently and effectively, and they need to be able to bring the solutions to the market quickly with the optimized cost. And finally, be able to port the applications to different solutions. This could be, for example, fielded solutions that have new standards or new upgrades. We want to be able to provide those solutions in the field relatively quickly and efficiently, or to be able to take common functionality and apply these features to a new product and be able to evolve new applications quickly and effectively. So if we take a snapshot of where the market stands with multi-core SoC platforms from a silicon perspective and how they're addressing some of these market requirements, we're seeing several exciting things. First of all, we're seeing higher performance, lower power consuming solutions in the market, and this is primarily due to the inclusion of multiple cores on a single yet more complex device. Now these cores can be of multiple types, that is, they can be a RISC-based CPU, a digital signal processor, or even a configurable functional processor implemented in hardware that's doing very efficient yet unique functionality. Overall, we're seeing a reduced bill of material cost. Again, this is primarily due to a higher level of integration that is taking solutions that had a board with multiple chips on it and including the functionality of all those chips into a single yet more complex device system on a chip. We're also seeing the ability to scale these solutions. Again, this is due to having multi-core applications as well as multi-chip devices that can be connected together, achieving higher performance. We're also seeing manufacturers address the time-to-market challenges. This is being done in several ways. First of all, offering software platform abstractions that we'll get into a little bit later in this discussion, it being able to allow the programmers to apply these to multiple solutions, as well as common platforms, that is multiple SoCs that are very similar in programming yet are optimized for each of the functionality and the solution spaces that they're targeted for. And then finally, tools that are enabling the software developers to provide these scalable solutions to the market quickly. And finally, we're also seeing application portability being addressed. Again, this is through software and platform abstraction, which we'll discuss a little bit later. I'd like now to take a little bit of time to talk specifically about what Texas Instruments is doing in the multi-core SoC space. The fundamental element of our TR multi-core strategy is the Keystone multi-core architecture. It's both an architecture and a palette of features, capabilities that we draw from to create devices for various market solutions. We're currently developing products based on the second generation of this architecture, is known as Keystone 2. From a customer perspective, Keystone is a comprehensive platform which includes the devices themselves, the Keystone software, and the Keystone tools. Together, we feel that this solution, this architecture, is addressing a lot of the scalability and application portability aspects of the marketplace requirements, as it provides the ability to have solutions that are optimized for key cost points and key performance points, while enabling the software developers to be able to have a very common platform and common tool suite and common software set that they're familiar with, achieving some of those challenging time-to-market goals. Now we'll take a detailed look at the Keystone multi-core architecture. First of all, the areas in red represent the chip infrastructure, that is the Multicore Navigator and its queue manager, which I'll talk about in a little bit. The TerraNet, which provides the connectivity between all of the elements, the processing elements, and the memory within the device itself. We believe that this is a very essential portion of the solution, this chip infrastructure, in that it's essential in providing multi-core entitlement to an SoC. That is the ability of all the processing elements within the device to perform 100% in parallel with each other as if they were standalone devices. Otherwise, you don't see the benefit, or the full benefit anyway, of the higher level of integration if performance is degraded by a weak chip infrastructure. We have elements called core packs, which include both DSP and ARM processors. And again, depending on which solution is being implemented or developed, we have a varying number of each of those devices. Obviously, a key part of the network, the chip architecture, is the memory, and multi-core share memory is a big part of our solution in terms of having it appropriately connected to all the processing elements, again, striving for high performance, non-blocking type of interface and processing functionality. In many cases, we can also include specialized accelerators, that is IP blocks that are configurable but implemented in hardware to reduce both power and size of a specific function that, while could be performed in a processor, again is more optimized in silicon execution. And this is primarily for packet processing. Any part of a solution that requires a network interface and Ethernet port would benefit from some type of fast path processing with the packet acceleration and security acceleration. And for our base station solutions, and even some of the cases in our mission critical functions, we have specified radio processing 3GP functionality. And of course, the I/O is essential too. High performance interfaces, SRIO, CPRI for the radio applications, and of course the Ethernet functionality, as well as integral switching. I'd like to take a moment now to focus on a feature of our Keystone architecture that plays an important role in the silicon side of today's webinar subject, and that again is the Multicore Navigator. The Multicore Navigator includes up to 32,000 queues, a queue manager, and a distributed packet DMA function that enables the software to process in a fire and forget mode of operation. It has a quality of service capability that allows for prioritization of tasks that then subsequently get scheduled for processing by various SoC processing elements, whether they be the DSPs, the ARM cores, or the accelerators that I just talked about earlier. Additional efficiency is afforded by the distributed nature of these queues within the SoC, providing for zero-copy memory transfer functionality. Now, this tasking to these queues can be done within a single SoC, that is a single Keystone multi-core chip, or done across multiple multi-core SoCs that are connected together. The Multicore Navigator effectively provides a hardware assist function to the application software for optimal use of the various processing elements of the Keystone multi-core SoC. And with that, I'll turn it over to Sven, who will discuss the software aspects of optimizing performance and portability in multi-core SoCs.
Thank you, Debbie. Let's talk about some of the programming challenges that comes with multicore. With a single processor, it may appear that we have concurrency, but actually everything happens sequentially. With multiple processors, however, we have true concurrency, and we have to make sure that they don't step on each other and compete for data. This means that if multiple cores share the same data, intercore locks have to be employed to protect the data being used by one core from being overwritten by another core. Multiple processing engines also means that synchronization may be required between them. As we heard from Debbie, multi-core SoCs driven by market requirements are becoming increasingly complex. The multi-aspect doesn't just apply to the number of cores, but also to the type of cores, including accelerators, operating systems, transport, and memory architectures. A key reason for using multi-core SoC is to increase performance within a given power envelope. To get this performance, we have to fully utilize the programmable cores, including DSPs, as well as accelerators for both data sharing and algorithms. You may have one application that needs to be used across a whole range of multi-core platforms. For example, in a product line with low, medium, and high-end products. Preferably, the application should run with little or no change on the different platforms, which requires that portability is part of the equation. You also need to consider if there is an available knowledge pool for the multi-core programming model of choice. To manage this complexity, we need to have a solid software and hardware infrastructure model. Looking at this bottoms up, we have the multi-core platform with different number and types of cores and accelerators, and above that we have software that helps us to manage the hardware platform. The software for this multi-core SoC platform includes operating systems and a collection of software components, including, for example, the Multicore Navigator software, low-level drivers, network software, and other things available through a software development kit. At this level, accessing the platform is made easier through the software components. Even so, further abstraction between the application and the underlying platform is desirable. Ideally, the application should be able to utilize all the capabilities of the SoC platform without being aware of how the components are invoked. Let's take a look at the situation from the application perspective. In many cases, a single application is used across multiple platforms in a product line, and those platforms may have different number of cores. Furthermore, this application is likely to be used at least as a starting point in the next generation product as well. It is therefore necessary to use a programming model that allows the kind of scalability required for multi-core platform support. Standards provide access to a broader ecosystem of runtime software and tools. They generally simplify portability, make it easier to move software investments forward into the future, and generally broaden the access to programming talent and expertise. We want easy access to the accelerators to achieve optimal performance and to meet project deadlines. Tools can provide an efficient way to apply abstraction between the application and the underlying platform, relieving the application from managing hardware differences. Different platforms may have different hardware components, different interconnects, and they can be on-chip or inter-chip. It boils down to that we want application portability that allows us to span a multitude of platforms and take full advantage of the capabilities offered by those platforms. So what would a suitable programming model for a multi-core platform be? Message passing is a model that meets a number of the key requirements for a multi-core platform. It has been used in networking and within operating systems for a long time and is therefore tried and tested in a variety of situations similar to a multi-core platform. We can expect the number of cores in multi-core platforms to keep going up to many cores in the not too distant future. Message passing is very scalable. It is often used in widely distributed systems with a combined total of many processors. We can also expect an increasing variety of cores, CPUs, DSPs, and an increasing range of accelerators for data sharing and algorithms. Message passing is generally agnostic to the underlying architecture and can handle this kind of heterogeneity quite well. It also comes in a few standardized variants, such as sockets in networking, MPI in widely distributed systems, and MCAPI in closely distributed systems. Messaging can be used for function isolation, which can be useful when dealing with legacy code and certified applications. It also provides a natural synchronization in that one function is operating on the data and then passing it along in a message to the next function. In shared memory systems, it's common to share data by reference, and in cases where local memories are used, the data has to be moved. Message passing can be done by reference by simply moving message pointers from one queue to another, or by data movement. Message passing has been used in computing for a long time, and functionality-wise it pretty much comes down to send and receive. So there is a large knowledge base of programmers available. Now let's talk about standards and some of the efforts going on in the Multicore Association. There are currently 6 working groups. The MCAPI or Multicore Communications API working group. It released version 2 of the MCAPI specification in 2011. The specification has over 2,000 downloads to date. The version 2 agenda is focusing in 2 areas, one being zero copy functionality both between application and driver as well as between nodes, and second being interoperability. Implementations are available from multiple vendors and MCAPI is gaining user adoption. The MRAPI or Multicore Resource Management API working group. It released version 1 of the MRAPI specification in 2011. The specification has close to 1,000 downloads to date. The MCAPI or Multicore Task Management API working group is working on version 1. The MPP or Multicore Programming Practices working group is in final review stages of its Multicore Programming Practices Guide. The TIWG or Tools Infrastructure Working Group is dealing with tools interoperability for embedded applications utilizing a common IDE. The MVWG or Multicore Virtualization Working Group is working on profiling different processor virtualization features. The Multicore Association membership represents a cross-section of the industry, including software vendors, silicon vendors, and device manufacturers, as well as academia. It spans producers, i.e. implementation providers, and consumers of the standards. This cross-functional group is working hard on simplifying utilization of and reducing time to market for multicore platforms. We encourage you to join the association and help make a difference in our industry. Specifically, what is MCAPI? It's a message passing based communications API targeting closely distributed computing, which consists of multiple cores on a chip or multiple chips on a board or any combination thereof. It's a source level API defined to allow implementations on a variety of different platforms, including those with limited resources, with or without an operating system, and systems with the real-time requirements. Communication endpoints are defined by a three-tuple consisting of a domain, a node, and a port. MCAPI has three communication modes: connectionless messages, which are the most flexible, providing buffered communication per message priority with blocking and non-blocking functionality. Example functions are send, receive, and available. Connected packet channels, also buffered communication with per channel priority unidirectional FIFO with blocking and non-blocking functionality. Example functions are connect, open, close, send, receive, and available. Connected scalar channels for 8, 16, 32, or 64-bit scalars. Per channel priority unidirectional FIFO with blocking functionality. Example functions are connect, open, close, send, receive, and available. Other functional areas include node and endpoint management, dealing with initialization, node properties, and creation, getting, attributes, and deletion of endpoints. We also have non-blocking management functions such as wait and cancel, and also a group for support functions. So where does MCAPI fit into our software-hardware infrastructure model? MCAPI provides an abstraction and can be used in the model that we discussed before. When we combine MCAPI with tools that help to manage the configuration of the underlying platform, we can take the abstraction to the next level. As you can see in this picture, the application can communicate between the different parts of the underlying platform via MCAPI. There may still be a need for the application to go directly to the underlying platform, but to a much lesser degree than without MCAPI. So far we have talked about programming model, standards, and software infrastructure. But how do you actually use message passing to multicore enable your application? It's actually quite simple. If you think about what to do on a single processor, you have functions that operate on data, and the data is passed into or out of the functions via parameters. If you take one or more of those functions and move to another core, the parameters will have to be communicated to or from that other core. This is done by encapsulating the one or more functions with communication calls. The parameters are sent off to that other core where they are received and fed into the one or more functions for processing. After the processing is done, the results are communicated to the appropriate recipient. So the process is encapsulate and distribute. Now let's discuss a use case for this method. Here we have on the left a number of programs or functions that are running on 6 separate processor chips on 2 separate boards. Our objective is to reduce the bill of materials and cost of our platform. We choose to consolidate these 6 separate processors onto 2 3-core processors. We encapsulate the functions with MCAPI calls as described, and then we distribute them onto the 2 3-core chips. The interconnect between the 3 cores on each chip happens to be shared memory, whereas the interconnect between the chips is rapid I/O. With the right combination of MCAPI and tools, we can achieve this without requiring the application to be aware of the core location and interconnects. If we have a different higher-end product in this line that has 8 cores on the same chip, we can take this MCAPI Enable source code and move it to the 8-core chip with little to no change. In this situation, we're only using 6 of the 8 cores, and we could either leave the 2 extra cores as reserves, or we could take one or more compute-intensive functions and duplicate them onto those extra cores, thereby increasing our performance. Using this approach, the application remains virtually unchanged. We have covered the encapsulation method and the use case. Let's talk about how you practically do it. Here we have one of the polyplatform tools that we can use to create what we refer to as instant MCAPI. The tool is topology aware, meaning that it knows what is available in the topology in terms of nodes and ports, which means that it will offer to the programmer only available nodes and ports. The programmer selects which MCAPI function he or she wants to use, selects the blocking or non-blocking version if applicable, and then selects the proper nodes and ports. In the next step, the programmer selects a set of variables, and when that's done, press finish, and the corresponding MCAPI code will be inserted into the application at the location specified by the programmer. This dramatically reduces the manual coding required to use MCAPI, as well as coding errors, reducing debugging effort and speeding up the process. Referring back to the software-hardware infrastructure, we discussed the benefits of MCAPI and the software development kits combined with tools. Equally important is that the toolboxes are well integrated and appears as one. What we see in this slide are the Code Composer Studio development kits tools, which are integrated with the polyplatform tools. This way the programmer can work on the multi-core platform from a single cockpit. In this slide we see the polyplatform mapping tool Polymapper. In the mapping tool, a topology consisting of nodes and links is laid out. The nodes represents a collection of one or more functions, and the links represents the data paths. Each node is assigned certain properties, including the type of processor and which operating system it's running on. The links are assigned properties relating to the interconnect used for the link. The one or more flows of an application are thus mapped to a topology. What you see in this picture to the left is the tree view of the topology, and to the right the graphical topology view of the nodes and the links. You can see the properties of topology objects in the property view by clicking on the objects in the tree or topology views. When a topology map is created, the wizard is used to provide choices for the programmer. It is also simple to add or remove nodes and links at any time. I mentioned the importance of access to acceleration for optimal performance. What we see here are two examples of links representing transports using accelerators for data movement. On top we see a shared memory link with DMA support. The programmer configures the link with a set of parameters and can specify when the DMA will be used and not by setting a trigger point. There is of course a cost of setting up a DMA transfer, and a soft copy may be more efficient to use for small transfers, hence the trigger. At the bottom we are looking at a serial rapid I/O link. This link utilizes the Multicore Navigator in the Keystone device, a combination of software and hardware acceleration that Debbie talked about, as well as the rapid I/O device. To use the rapid I/O link, the programmer fills in a few parameters, such as for example rapid I/O type 9 or type 11, and apply changes, and it's good to go. As we can see here, accessing those hardware accelerators is simply a configuration effort rather than a programming effort, which can save a lot of time. The things we have talked about so far boils down to portability on powerful and complex multi-core SoC platforms. So let's talk about a concrete portability example. What you see in this picture is an MCAPI enabled application that we run first on x86 and Windows, and then on TI C66XX and DSP BIOS. It is the same application, and this is all done from within the TI Code Composer Studio environment. Separate projects within the workspace are set up for Windows and DSP BIOS. The application is linked from one project to another. There is a small portion of the application that is used to set up the environment for DSP BIOS, which is not used for the Windows environment, but the source code is identical. So technically, if you have algorithms that are not operating system specific, you could develop and test the functionality on Windows and then deploy on C66XX and DSP BIOS. As discussed before, it's the combination of MCAPI and tools that provides this level of abstraction and portability. What we see in the picture are the two different topologies, the one for x86 and Windows to the left, and the one for C66XX and DSP BIOS to the right. As you can see, the only difference in the node properties are the operating systems and processor types. So now you may be thinking, is that really the only difference? Well, not quite. There is one more thing. We also have to specify the transport being used for the links in the respective topology. Both links are using shared memory, but there are some differences based on the underlying platform. And that's really all there is to it. If you're interested to learn more about this, there is a related video that shows going from x86 and Windows to TI C6474 and DSP BIOS platform. You can find it at this link. So what do we take away from this? Market requirements are driving continuous performance improvements within a given power envelope, an increase in consolidation with more and more functionality on a single chip. This comes with increasing complexity and more challenges in harnessing the increased capabilities. The solution is to combine multi-core SoCs with proper standardized programming models such as MCAPI and the right combination of tools. If the tools components are coming from different vendors, they should preferably be well integrated, provide the proper level of abstraction and access to the acceleration offered by the platform. Application portability can be achieved with the right combination of SoC platforms, programming models and tools as discussed today, which will save time and money today and in the future. Thank you for joining us today. We will turn to question and answers momentarily. If you have any further questions directly for any of us, please send us an email. You will find our email addresses on slide 1, and the slides will be posted on the Multicore Association website.